Hi guys, and welcome to the next in the series of videos on production of materials, and we're looking at radioactivity. In this case, we're going to have a look at some of the uses of radioisotopes, and specifically with the Australian nuclear reactor focus. So the reason that we've got this particular topic in our production of materials section is because radioisotopes have a very wide variety of uses, particularly in both industry and in medicine. And at ANSTO, the Australian Nuclear Science and Technology Organisation, that's where they have a number of different reactors which are used to generate a range of different radioisotopes that are probably primarily used, but not exclusively used, for medical purposes. The problem is that most of these radioisotopes are not natural. They have to be synthesized. So in this little video, we're going to have a look at how some of them are made. There's two main ways that we can produce artificial isotopes, and they are in nuclear reactors, and often that involves neutron bombardment, or particle accelerators. And this is usually firing alpha particles or heavy nuclei at other particles or at other nuclei in order to try and get some sort of large atom to form. So some of the transuranic elements we'll look at in one of the other videos will be a specific application of particle accelerators. Firstly, the nuclear reactors. Nuclear reactors are used to either generate power, and Australia has had a history of bipartisan, I'll call it, support for no nuclear power generation in the country. So whilst we have a very large deposits of uranium in our country, we tend to export them to countries who use them to generate power. What we tend to do with them is we use them to create other isotopes. So inside the nuclear reactor, there are a series of reactions where we can break down the uranium-235 into smaller elements through fission reactions. So fission just means split, and fission reactions are what enable us to create, say, krypton and barium from one unstable uranium atom. The process, fairly straightforward. Uranium-235 absorbs a neutron, so it's going to take in a neutron, and it fissions into two new atoms and three neutrons. And this is where we get what we call a chain reaction. So the chain reaction is a consequence of one initial neutron providing us with the opportunity to split into or produce three additional neutrons, and so they can therefore bang into other uranium nuclei and keep this process going. One of the neutrons is absorbed by an atom of uranium-238, so this one over here. Another neutron is simply lost, so it just disappears into usually the control rods or the cooling fluids, which may include things like heavy water. And one collides with an atom of uranium-235, which then repeats the process. So this is our chain reaction. Both of the neutrons collide with uranium-235, each of which undergoes fission, releasing between 1 and 3 neutrons, and so we have this cascade sort of effect as we go down along this chain. The nuclear fission or breaking down that occurs in nuclear reactors is one which generates very large amounts of energy, and that is according to Einstein's probably most famous equation that everyone seems to know, E equals mc squared, which is the conversion of energy into mass or mass into energy. And in this case, that's what we're interested in. converting that mass into the release of large amounts of energy. The consequence of that is that you need to have some sort of control measures in order to make sure that that energy release is regulated. If we use these radioisotopes to generate power, then we can obviously generate large amounts of electricity, provided we can control the way that they are being released. And I guess the extreme case of unregulated energy release from nuclear power is the atomic bomb. Now, nuclear reactors can create commercial radioisotopes for us in one of two ways, either by what we call neutron capture or by fission products. And hopefully you've already got a sense of these now. So the first of these is neutron capture. Neutrons that are released during the fission of radioisotopes like the uranium-238 that we looked at before are used to create some commercially important radioisotopes. One of those is cobalt-60. We fire neutrons into the nucleus of our target atom. So in this case, that would be, for example, the cobalt-59. So this is cobalt-59. And what we do is we power in a neutron that's been released, say, by the fission of uranium, and we produce a cobalt-60 isotope. Now, the cobalt-60 is unstable and will undergo radioactive decay, releasing a beta and a gamma particle, or gamma ray, beta particle and a gamma ray, beta negative. And this is one of the useful products. The original decay process is very energetic, and so therefore when cobalt-59 accepts a neutron into its nucleus, it will, the cobalt-60 produced will also have associated with it a little bit of gamma radiation release as well. There's a differing amount of energy that's available in the nucleus during the processes of neutron capture or fission, and this comes out in the form, generally speaking, of gamma radiation. The alternative to neutron capture is fission production. So this is taking a large radioisotope like uranium-235 and splitting it up into two smaller nuclei. This is an important process for the production of some very important commercial radioisotopes that occur in the medical and industrial fields. One important one made this way is molybdenum-99. The importance of molybdenum-99 is that it is a radioisotope, and it will decay to form technetium-99m. And this one is a very high energy radioisotope which decays through gamma decay and makes it very, very useful medical isotope. One that is very well worth having a look at as a good example, and one which, if we do visit ANSTO, you'll get a chance to have a look at there. It's produced when uranium-235 is bombarded with a neutron, but that neutron causes the uranium to split, to undergo fission. Molybdenum-99 is one of the very important products, and in addition to that will be tin-134, and also 3 neutrons. There is an amount of energy that's associated with this particular process, and that's released as gamma radiation. But it's the molybdenum-99 that is very important, and often it's used as a high energy source and transported in that way, so that when it reaches hospitals or diagnostic centers, by that stage it will be able to be used, as it's already started to then decay into the diagnostic tool, technetium-99. So this is the area where, when the questions come up, they can be quite long and in-depth, and so it's very important that you have 2 radioisotopes that you can talk about in industry, one for industry and one for medicine. So in 2007, question 19 was a 7-mark question, so a really big one, and these are the ones that we need to plan and prepare for. Many benefits and problems associated with the use of radioisotopes in industry and medicine. We need to evaluate the impact on society of the use of radioisotopes in both industry and medicine. In your answer, we need to give examples of specific radioisotopes making reference to their chemical properties. So there's a lot of components in this question, and it requires a bit of organization. In the report that came out from 2007, a few observations were made. Better responses, so the 6 to 7 mark responses, indicated a thorough knowledge of both the characteristics of the individual isotopes and the link between how the properties relate to the use. And all of these things are very, very important for you to include in your answer. It's also an evaluate question, so there had to be some evaluation present in there and some decision made with hopefully some supporting argument. One of the very key things is the evidence of planning, and it's hard to overstress the importance for these really long questions of thinking through how you're going to put your response together. So when you're doing something like this, it's really important that you evaluate. So you come up with a decision first of all. Okay, very important. Radioisotopes are very important in industry and/or medicine. That needs to be very clear, and that point needs to be argued through everything else that you put together. You need to have your industry example, and preferably with a nuclear equation to show how it was formed, and also your medical example with, again, a nuclear equation. So you could, for example, pick technetium-99m and how it's formed and how it breaks down. Now, the importance is the link between properties and use. So there are 3 areas that you need to make sure that you're including for each of these examples. So you need to talk about half-life. How quickly does the radioisotope break down? You need to talk about ionizing ability, because the ionizing ability is going to contribute to whether or not to the types of potential damage that could be caused to other atoms that are present in the system. This is particularly important for medical use. And we also want to talk about penetrating power. Now, in addition, there are a couple of other things that sometimes get lost. For example, you may, for your medical example, choose something like iodine, and you want iodine to move through the body system and collect in the thyroid. But in order for that to happen, you need to make sure that it's a soluble form. So if I'm going to take it or drink it or have it injected or something like that, then I need to make sure that the form of the radioisotope is actually in such a way that it will actually move through my body and be taken up by the target organs. So there are a number of factors that you want to consider when you're working through these, and you need to make sure that you link short half-lives or longer half-lives, high or low ionizing ability, high or low penetrating power to our detector. How are we detecting gas leaks? How are we detecting cancerous cells? How are we targeting specific cells that we want to treat? So these questions are large mark questions, and they require a little bit more thought, but with good planning and even writing something like this out before you even start writing your answer can be a good way of maximizing your return. Thanks for watching.